Hi everyone. Can you see the whiteboard?
Yes, ma'am.
Yes.
Okay. Sure.
Ma'am,
So yeah. So let me start the class. So before I start the class, the one thing that I wanted to discuss is that there is this extra hour, right? Which is, I guess, Saturday 9:30 to 12. Okay. So, but what I'm planning right now is that since we are already interacting for 4 hours, I thought not take the 1.5 hour, but instead we have to do this weekly evaluation. So, which will happen on Saturday, say for half an hour to 45 minutes. So is that okay with all of you?
ma'am, can you repeat it?
Yeah.
We are
Yeah.
not audible in the middle.
Yeah. Can you hear me now?
Ma'am, it's very soft, ma'am.
Your voice is low.
Yeah.
Can you hear me now better? Hello. Hello.
Ma'am, you are audible.
Yeah. Okay. Fine. So what I'm saying is that we will on we have this extra slot on Saturday where we are going to have the weekly evaluation. Okay. Say for half an hour to 45 minutes on Saturday. So is that okay? I will send all this to detail via email, but I just wanted to tell you all now that Saturday, say 9:30, we can make it for 10 o'clock also if you wish to. So it will just be for half an hour to 45 minutes. Okay. And that's the only way we are going to use the extra slot. Fine.
Ma'am, I think the extra slot on Saturday is 10:30 to 12.
Okay, fine. Then it's fine. I'll just check it once. I'll send an email to all of you. Okay. So
Yes.
around 10:30 we will have this evaluation over Moodle. Okay. So how it will usually done this way. I'll post one or two questions and I'll give you a slot of half an hour. You have to solve the question and take a picture and upload it in Moodle. Okay. The link given in Moodle. Okay. That's how we are planning it. Okay, fine. Now, getting into okay, so getting into the uh, derivation. So let us get back to torsion of circular. Okay, let me call the torque as M. Okay, so we were here where we said that there is no out of plane deformation, there is no distortion of the circular cross section in torque, and the shaft is in pure shear due to applied torque MT. Okay, so now we are going to see what would be the solution and whether the solution that we are assuming is satisfying the equations of equilibrium. Okay, so it has been observed experimentally that the if we take a circular shaft and apply a torque or a twisting moment of MT, the only shear that is going to be produced in the only stress that is going to be produced in the shaft is going to be a shear stress. Okay, and it has also been, and the theory is that the shear force at where theta is the rate of twist, and this is constant. If this is the shear stress, okay, and the shear strain is
Ma'am, what is theta?
theta is the rate of twist, d phi by dz. Phi is the angle.
Okay, but I thought you said that phi is the rate of twist because phi will be twist by length.
No, theta will be twist by length. That's why this is dimensionally constant. See, Newton per meter square, R and L.
Okay, okay. Then what is phi, ma'am?
Phi is d phi by dz. Phi is angle of twist. Theta
Okay,
is rate of twist, d phi
okay,
by dz.
got
Okay,
it.
okay. So the shear strain is theta into R. Now let us see. So this is given in the polar coordinate. So let us see what is going to happen if we transform this into the Cartesian coordinate. Okay, let us see how this stress is distributed and how are we going to convert it into the Cartesian coordinate. So now if this is the shear stress, then let me try to draw the shear stress. So the shear stress okay. So at a radial distance r from the origin O, at a radial distance r from the origin O, the shear stress it is at a tangential direction or perpendicular to the radial direction and is given as g into theta into r. Okay. So the entire shear stress distribution is going to look something like this. This is your entire stress distribution all over, right? At every radius that you can consider, you are going to get this. Okay, so this is how the shear stress is distributed. Now, if I try to write this shear stress in terms of the Cartesian coordinate, then what do I get? I get tau, xz is going to be, so let me just resolve this in x and y direction. Let me just erase this off. Okay. Okay. So this is now. So this shear stress can be thought of having two components, tau in x and y direction, which is tau yz and tau xz, right? According to the definition of the shear stresses, tau xz and tau yz. Okay. So now if I try to write what is tau xz is minus g theta r into sine theta. Okay. And tau yz is g theta cos phi. Sorry. Okay. Is this fine? Okay. Because tau xz is in the opposite direction. I have this minus sign, and so this is tau yz. Now this can be further written as minus g theta r in by y by r. Okay, but because sine phi is nothing but y by r, and so this is minus g theta y, and tau yz is going to be g theta r x by r, and that is going to be g into theta into x. Okay, is this clear? Anyone has any questions here? Right. So if this is the expression of the two shear stresses, then I can write down the entire stresses as my all normal stresses. Sigma x, sigma y, and sigma z is 0. My tau xy is 0. Only tau xz is minus g theta y, and tau yz is g theta x. Okay, right? So this is my value of the stress component. Then I have
Ma'am, you are not audible.
Yes, ma'am, lost your voice.
let me just change the mic into a lapel mic. Just give me a few moments. Yeah, can you hear me better now? Can you hear me?
Yes, ma'am.
Yes,
Okay.
ma'am.
Yes, ma'am.
Is it better? Or is
Yes.
it?
Yeah.
See. Let me take a pause here. See, I don't know. I mean, this is creating a lot of issue. Do you think it's a good idea to record and then show it to y'all? I don't know. This internet connection is probably causing all these issues. So maybe I will see for one or two classes and then move on to recording and then showing it to y'all later. That probably is a better solution. Anyway, so I will see for one or two more classes and probably move into recording. So anyway, so let's get back to. So let us get back to where we were. So please stop me whenever you can't listen me or my voice is feeble. I guess that's not because of my mind, it's because of the internet connection. So I will stop and try to restart again. Fine. So so these are the stress component that we were. Can you see my whiteboard?
Yes, ma'am.
Yeah. Okay. So so these are the stress component in a circular shaft with the applied torque. Now, if I try to see, so this is what we have. Let me just summarize what we have done. Okay. So from experiment, it has been observed that all the features of the torsion of a circular shaft that I discussed in the last class is derived from experiment. Okay, and based on this experimental finding, Coulomb found out that this is the solution for this. This is the solution for the torsion of a circular shaft. So now what we are trying to do is to see that this solution, which was derived by Coulomb, okay, from the experimental finding, whether it is satisfying the equations of elasticity, okay, that we have to see now. Okay, the entire derivation is given in Timoshenko and Goodyear theory of elasticity in a very nice way. It's a very good read. So any of you who wish to read, it's also available online. Okay, I have an online copy. There are several online copies available in the internet. To download on all those, download those copies, and there is a chapter 5 which is called General Theorems of Elasticity. That's a good read. And there is a chapter 8 or 10. Sorry, chapter 8 is on the theory of elasticity and chapter 10 is on torsion, which we are going to thoroughly follow in the next couple of weeks. So anyone who wish to read probably should look into the book on Timoshenko. Fine. So now, so again, to reiterate, now our job is to see that whether this solution satisfies the equations of elasticity and is a true solution. So let us go to that problem. Okay, so now let us see. So again, let me just write down all stresses are zero except tau xz, which is minus g theta y, and tau yz, which is g theta x. Okay, now let me write down the equations of equilibrium. Now this is the body force. which is 0 because there is no externally applied body force. So this is 0. Now this is equal to 0. Sigma x is 0. We know tau xy is 0. Now tau xz by del z is 0 because tau xz is just a function of y. So this is also equal to 0. Okay, so this whole thing is getting satisfied. So the first equation of equilibrium is satisfied. Now let us look into the second equation. So this is also satisfied. Now let us see what is tau xz by del x. Tau xz by del z is also equal to 0. This is also equal to 0. So this is also satisfied. Okay. So this solution is satisfying the equation of equilibrium. Now let us see whether it is satisfying the boundary condition. Okay.
Ma'am, I have a doubt.
Yeah.
Ma'am, so why is the body force 0? I mean, there's a weight, right? The weight of the shaft.
So yeah. So what we are doing is that right now we are neglecting the weight.
Okay, ma'am.
Okay, right now we are neglecting the weight. We are just assuming that it is a pure torsion problem. Okay, just the torsional moment is acting.
Okay, ma'am.
Okay, nothing else. Yeah, so let me now go into the boundary condition. Okay, so what is the boundary condition? Let us understand first. What is the boundary condition? So there is no applied force on the lateral surface of the shaft. So let me just draw the shaft. Okay. So this is the only force that is acting is the torque. Okay, the torque mt, and the lateral surface is free from any force, right? The lateral cylindrical surface of the shaft is free from any force. The top and bottom surface is also free from any force. The only externally applied force that is acting is the torque mt, force or moment. Okay? That is acting is the mt. So now let us see whether our stress system, the solution that we have got, is satisfying this boundary condition. Okay, is satisfying this stress, the free boundary condition on the lateral surface and the top and bottom surface. Okay, now let us first write down the boundary conditions on the lateral surfaces. Okay, so now what do I have on lateral surfaces? If I write down the boundary condition, it is x hat, which is the force, surface force per area, is sigma x. This is 0. Okay, so if I look into the first boundary condition, the externally applied force x hat is 0, sigma x is anyway 0, tau xy is 0, tau xz is not equal to 0. But what about n? Can someone tell me what is the value of the small n for lateral surfaces?
It's cos 90, ma'am.
Cos 90. So therefore it is 0, right? Because on the lateral surface, if I see the normal n, what is small n? Small n is cos of n with z. Okay. The angle n, the normal n is making an angle of 90 degree with the axis z. Therefore, small n is equal to 0 for the lateral surface. Okay. So this boundary condition is identically satisfied. Okay. So this has been satisfied. Now let us go into the next boundary condition. Okay. So now tell me, what is the value of this boundary condition? So is this equal to 0? Just let me know.
Yes, ma'am.
This is equal to 0, right? Because L is going to be y by r, M is going to be L is going to be x by r, and y is going to be M is going to be y by r. So I can okay. So the third boundary condition is also identically satisfied. Okay. So the solution that we are working with satisfies the boundary condition on the lateral surfaces. Okay. Now let us look into the boundary condition on the top and bottom surfaces. Now let us look into this. Okay, so sigma x is equal to 0, tau xy is equal to 0. So I have this as tau xz. Okay, n is equal to 1 for this particular case. Okay, so I have x hat is equal to tau xz, y hat
Ma'am, won't tau xz into n, won't n be -1 for the bottom surface?
So see, this will be now. Okay, I should talk about it. See, the sign convention is going to just the signs, not the convention. The signs are going to just flip for the top and bottom surface, right? So though n will become -1, your tau xz is also going to be of the negative side.
Yes, ma'am. Okay.
Okay, so that is going to remain conserved.
Yes, ma'am.
Okay, so now I have y hat is equal to tau yz. Then I have there's some issues again. Just hold on. Okay, so now if we look into the third boundary condition, this is going to be 0. Now sigma z is going to be 0, L is going to be 0, and M is going to be 0. Okay, for the top and bottom surfaces. So can you hear me?
Yes, sir.
Yes.
Okay,
Yes.
okay, fine. So this is identically equal to 0. So we don't have to bother about this equation. This is solved. So now what am I left with? Okay, so unlike my lateral surfaces, my top and bottom surfaces are free from any externally applied load, the boundary conditions obtained from the solution that we have adopted is not getting satisfied, right? See, what is happening physically? Physically, these two are 0. X hat and Y hat are 0. But if x hat and y hat are 0, my boundary conditions on the top and bottom surfaces are not getting satisfied. Okay. So ideally, the solution that I have adopted, or I mean, what Coulomb have suggested, is not a true solution, because it is not a true solution of the boundary condition on the top and bottom surfaces. Okay, but now let us see why it is practically a good solution, why it is a practically feasible solution. Okay, now, so according to this boundary condition, what should be the normal, what should be the force distribution on the top and bottom surfaces? So this is a bit tricky. You ask me any question if you don't understand. Let me complete this part and then you ask me any question if you don't understand. Okay, I'll just reiterate. According to the solution that we have adopted, the top and bottom surfaces cannot be free from force because of these two conditions. It should not be. If it is free from force, it's not the true solution. Okay, but in real case, there is no externally applied force on the top and bottom surface. What we have is only the torque, mt. Okay. Now, but what we are going to see now, what we are going to try to understand, that this is a practically good solution. So practically, the solution is a acceptable solution. Okay. Let us see how. Okay. Let me erase this off. Now, the resultant of this force is going to be the resultant of x hat and y hat. It is this f hat resultant. Okay. So if you see f hat resultant, it is a normal force in the, it's a tangential force. Okay. And if you see, so therefore, if I see the resultant of the externally applied force, it should be distributed in this way. Okay. So therefore, the on the to have the real solution, the problem should have been this: the top and bottom surface should have an external force distribution given by the red color distribution. Okay, but that is not happening in the real case. So now you can see that this red color force distribution, the resultant of this red color force distribution is 0. Okay, summation of f at r, the vector summation, is equal to 0. Okay, what it results, this force r results in a torque. So mt, or the applied torque, should be distributed okay. So So let me just try to explain this. See, the red color distribution is how the force should be applied at the top and bottom surface. Now you can see that the resultant of this force distribution is 0. Okay, the force distribution, the effect of the force distribution is a torque. Okay, now what Coulomb's theory has said that ideally the torque mt that is applied should be applied through this kind of stress distribution. Okay, but in real life case, it is not applied in this form of stress distribution. It is just applied by some pure torque mt. But now the idea is that there is something called a Saint-Venant's principle, which says that the effect of the boundary condition diminishes in a small vicinity of the boundary. Okay, so whether I am applying the torque in form of a pure twist moment or whether I'm applying the torque in form of this red color force distribution, it will not matter well inside the shaft. The stress distribution that is going to happen well inside the shaft is not going to be disturbed or affected by the way we apply the torque. Whether we apply the torque the way it is applied in real case, the pure torsional moment, or whether I apply the torque in form of this red color force distribution. It will not matter inside the shaft, okay, well beyond the boundary of the shaft. Yes.
Ma'am?
Yeah.
Ma'am, how do we apply the torque in this red color?
We don't. Okay. But the solution requires, ideal solution requires you to apply the torque in this. Okay. So can you understand this point that this red color distribution is what should be the boundary force? Okay. And the effect of this boundary force is a torque because the resultant force of this system is 0. The only effect is a torque, right? You can understand that.
Ma'am, can you please repeat that boundary condition theorem once more?
The boundary condition theorem that x hat and y hat.
No, ma'am, you told that something effect of boundary
Okay.
condition.
So there is Saint-Venant's principle. Okay, so Saint-Venant's principle is one of the earliest theorem of solid mechanics. It states that any change in the boundary is perceptible only in the small vicinity of the boundary, in the blue region that I have marked. Okay, So whether I am applying the torque in form of a pure twist in the case 2, or whether I'm applying the torque in form of this red color force distribution, the changes will be only in the small vicinity of the boundary, in the 2 blue color region. Okay, the changes on stress distribution will not be prominent in the inside location of the shaft. Okay, this is not only for torsion, this is for any solid mechanics or structural mechanics problem. Okay, Saint-Venant's principle is a versatile principle. It's kind of an axiom, okay, which applies to any solid mechanics problem. That any change in boundary is perceptible only in the boundary region of the structure, not inside the domain of the structure. Is that clear?
Yes, ma'am.
Okay, so so now my point is that whether we apply the torque in form of pure torsion or through this stress distribution, which is the real solution, doesn't matter. So if we in real life we cannot apply the torque in this form, this is not realistic. Okay, this is more
Which
realistic.
one is not realistic?
Applying the torque in this force distribution is not realistic. We don't do it that way.
Okay.
Okay, I mean, you can't think of a practical example where the torque is applied in this nice distributed pattern. No, it's not happen. It doesn't happen. Okay, this is more realistic. Okay, okay. So my take is that even if we apply the torque in this way, the stress distribution that we have studied is not going to get hampered in the internal domain of the shaft. There might be a small change in the boundary region, but not inside. Okay, and you should keep this Saint-Venant's principle in mind. This is kind of an axiom of solid mechanics. Okay, it applies to almost all solid mechanics problems that you can think of. There is no proof of this, but this is an experimentally observed phenomena, and it happens in almost all cases that you can think of. Okay, linear, non-linear, whatever. Fine. Okay. So any questions here?
Ma'am,
Okay. So yeah.
does that mean if we take a section in the middle of the shaft and if we observe the force distribution, or I mean how the moment distribution is, can we say it is in the form of forces?
Wait. If you take a section in the middle of the shaft, there is no force there. There is only stress.
Okay.
Right. Inside you don't have any force. Force is only on the boundary or a body force. Right? That's how we can apply the force. The force can either be a body force or an externally applied force, a surface force on the boundary. So when you take a cross section, it is only stress. And for this case, it is pure shear stress, tau xz and tau yz. So to answer your question, if I take a section somewhere inside, the stress distribution is not going to change. Whether you apply a torque in this way or that way, in first way or in second way. Did I answer your question?
Ma'am, the shear stress caused in the middle, will it be in the form of force distribution, or the second case, more realistic case?
So if I take a cross section, let me do this. If I take a section here,
Yes, ma'am.
A1, and a section here, which I call A2. Okay, now let me erase this. right?
Yes, ma'am.
Is this clear now?
Yes, ma'am.
Okay, fine. So whether I take whether the section is A11 or A22, the stress distribution is going to be exactly the same for both. Stress distribution is going to be of this form. It will be the resultant of tau xz and tau yz, which is going to be tau r, which is g theta. Fine.
Okay.
Okay.
Yes.
So let me move into the next part, which is the strain displacement relation. Okay, so strain displacement relation is
Ma'am, can we have a break?
yeah. So shall I just end this part and then take a break, and or you want to take a break now? Okay, let us end it now and then come back after. So it is 9 o'clock in my watch. So around 9:07. Is that okay?
Yes, ma'am.
Okay, fine. Thank you.
Yes, ma'am.